Welcome back to the final video in the tutorial series for Prisms-Fatigue. In this video, we will generate a computational multiaxial fatigue gamma plane. The data we will work with is also available at the Materials Commons link. So to access this, we first go to the Prisms Center page and click on the Fatigue repository. The link in the description, doi.org, under Datasets, will take us to the Materials Common page, and this can be once again downloaded using Globus. The multiaxial gamma plane is an important consideration in the design of engineering components. The majority of fatigue experiments are done in simple uniaxial states of strain. This is primarily because these types of experiments are easy to perform. However, a lot of engineering components seldom undergo simple uniaxial strain states. They might experience biaxial or shear loading as well. So the multiaxial gamma plane attempts to characterize the fatigue behavior across these three possible strain states, but it also considers different strain magnitudes. On the bottom left, I'm showing a gamma plane as formulated by Brown and Miller back in 1973. The first thing to notice is these contours. So these are called iso-life contours. These basically represent the same fatigue life for a given material. Now there are a set of boundaries on this gamma plane. So the bottom boundary here corresponds to equibiaxial loading. The top boundary corresponds to uniaxial loading, and the middle in the x-axis here corresponds to pure shear. One way to interpret these iso-life contours is to consider the requirement of a single engineering component. If this component must withstand 1,000 cycles, then we could determine the allowable strain in equibiaxial, uniaxial, and pure shear loading, and theoretically everything in between by interpolating these curves. It's easy to see why a figure like this would be beneficial to design engineers, although one should note that these are very expensive to make experimentally. If we consider a single fatigue experiment done in uniaxial tension in the high cycle fatigue regime, we would want to do multiple experiments to capture the inherent scatter in the fatigue response. This means that if we want to get multiple points on this plot for the purpose of interpolating contours, we need to do multiple experiments, perhaps 5 or 10, at each one of these points. We can instead create a computational gamma plane using simulations instead of experiments. We can generate a single ensemble of microstructures, or perhaps one very, very large microstructure, and then simulate this at a series of strain states and magnitudes. This is what I'm showing here on the right-hand side. So the way this iso-Fip contour plot was generated was by first generating 10 microstructures in Dream 3D, simulating them in Prisms-plasticity at a variety of strain states and magnitudes, and then using these Fips in a Gaussian process regression model. I have the gamma plane.py script open on the left-hand side, but before we go into that, let's look at the folders that were included in Materials Common download in the folder entitled Multiaxial Fatigue. This folder contains 95 other folders. It also contains a folder called Instantiation Data and Simulation Files. In Instantiation Data, we have the microstructure information for the 10 microstructures that were used in the generation of the gamma plane in the Prisms-Fatigue manuscript. So we have all the same types of files that we previously discussed. In the folder entitled Simulation Files, we have the text files necessary to simulate these 10 microstructures in Prisms-plasticity. There are two things that are missing here. The first is the PRM file, and the other is the .cc files. As I mentioned in the other videos, we need to navigate to the Prisms Center page on GitHub, click on the Fatigue repository, click on Source, and then Material Models. And here we have the three .cc unique files for Prisms-plasticity. So we need to take these and replace these with the source files for plasticity, source, material models, crystal plasticity. So there are default files here that we need to remove and include the ones included in the Prisms-Fatigue repository. In terms of the PRM files, we will find these in each one of these folders. So we have 95 folders, and we'll take a look at one of them. So what this has the results maxcomp and max10 files for this set of 10 microstructures. We have the PRM file in here as well. So why are there 95 folders here? To investigate this, please open up the multiaxial load parameters Excel sheet. So this sheet lists the combinations of strain state and magnitude that was applied to the 10 microstructures. So each one of these numbers in orange, these range from 0 to 94. So there's 95 in total. The first 9 indicate simulations that had pure uniaxial state of strain. So for instance, folder 0 says 0.72. So if we navigate to the same folder and we open up the PRM file, we will see that in this line of code here, this is where we are specifying the applied strain of 0.0072. In this case, we're arbitrarily saying that the size of the microstructure is 1 in each direction to make it easier to apply these strains for the other 94 folders. As another note, these simulations for the gamma plane have 30 elements cubed instead of 29. So for each one of these descriptions here, 0 through 94, we have an associated folder. So what this means is that for 18, where it says 18 in orange, the 10 microstructures were simulated to equibiaxial strain to a strain amplitude of 0.73%. And these files would be in folder 18 with the results maxcomp and max10 across that final straining cycle like we discussed in the calculate Fips.py video. So to summarize that, we take this list of 10 grain ID and orientations.txt files, and every unique PRM file in the numbered folder will allow us to simulate the exact same state of strain in terms of magnitude and whether it's uniaxial, biaxial, or shear to replicate the results in the Prisms-Fatigue manuscript. So the first folders from 0 to 28 have uniaxial, equibiaxial, and pure shear states of strain, whereas the remainder have case A and case B strains. And that is so we can populate the entire gamma plane, not just along the top and bottom and horizontal boundaries. Another reminder is that for these simulations to be proper for the generation of a gamma plane, all of them are run with this third type of boundary condition, where we are periodic in the z and the x direction and non-periodic in the y direction. This is because to locate the simulations on the gamma plane, we need to compute the plastic strain tensor and then the principal plastic strain tensor values relative to the free surface. Another minor note is that we only specify one value for these first folders, whereas for case A and case B, we say ratio in X and ratio in Z. What this means is that for the case of folder 29, we apply the full strain amplitude of 0.613% for the X, but only 0.5 times 0.613 in the Z. So we are changing how much of the strain we apply in both x and the z direction. These case A strains correspond then to a state of shear, because we will initiate the simulation with compression in the x and with tension in the z. And then for case B, we see at the bottom here that for these folders, we initiate in compression for both x and the z. But for some of these case B strain states, we initiate in compression, but pull in tension in the z. And users may ask themselves why this is the case. And this is basically due to the Poisson's effect. You can imagine that if you compress this material in the x, it will want to expand in the z. But if we are prescribing that it can only expand by 0.3 times the strain amplitude in the z, then we will be imposing a state of biaxial strain because the material wants to expand more. It's easiest to think about this for folders 68 through 74. Because if you apply a full strain, compressive strain in the x of 0.721, for instance, but prohibit the expansion or compression of the material in the z, then you will be compressing it in the z. And this will cause a state of biaxial strain. Now that we have discussed what the structure of the folders is like, we can start to compute the Fips and volume average them, and then generate the gamma plane. So first, we will go back to the calculate Fips.py script. I mentioned in earlier videos that we have these parameters here for the gamma plane that we previously set to false. Well, now we will set these to true. Let's go through the rest of the variables. The next thing we must set is the directory that contains all these numbered folders. So that is entitled Multiaxial Fatigue _ aluminum 7075 T6. So I will replace that as such. Next, we have to specify the shape or number of voxels for each instantiation. So this is 30 in the X, Y, and the Z. We then say we have 10 instantiations, and we will calculate the Fatemi-Sosi Fip with these variables here. We can actually get rid of this because that was for sake of demonstration in a previous video, so we no longer need that. We still have 12 slip systems, and in this case we're going to set gamma plane simulations to true, and we will set the number of gamma plane folders to 95 because we have 95 folders in total that range from 0 to 94. We need to set VTK visualize Fip to false because previously we had one VTK file that we could make a copy of and append. And in this case, what we have is just a single set of VTK files. So currently the code does not support to append the Fips to these VTK files and to then save them in these individual folders, but this may be a future update. So click save, and we are now ready to execute the script. And what it will do is, because we set gamma plane to true, instead of going to individual folders with a unique name like last time, where it might have gone into the cubic equiaxed free surface and calculated the Fips, by setting this to true, we will go to the multiaxial fatigue folder, and we will go through each of these folders numbered 0 through 94. So let's see how that works. Type in Python calculate Fips.py, and what it will list here is simply the folder that it's currently working with. So now when we go into the folder, we see that we have this new .p file that has the Fips calculated using the maxcomp and max10 CSV file. We also have an additional file called EP_averaged_0. So in calculate Fips.py, if gamma plane simulations is set to true, we actually go to another section of the import prisms data function. all the way at the bottom. So before I explain this, let me explain what is unique about these .csv files from the gamma plane simulations. So let's open one of these up. So these are similar to the ones I previously described, where we have the grain ID and then the X, Y, and Z position in the first 4 columns. The next 12 are then the current value of plastic shear strain on slip systems 1 through 12. And the 12 after that are the stress values normal to those slip planes. So we have additional columns here. So what these are the values of the plastic strain tensor. And we have these in the directions 1, 1, 1, 2, 1, 3, and so on. So basically what we have is the plastic strain tensor in the X, Y, and Z directions for the microstructure. And we have these for each individual quadrature output. The last column is the cumulative plastic strain output. So we need these because we actually use these to locate each simulation on the gamma plane. Because you'll see that the X and Y position is determined by the principal plastic strains. So in this code, what we do is we read these values at the points of max compression and max tension. So that is columns 28 through 37. And we average these over the entire instantiation. So let's open one of these new CSV files. So in this case, what I have is the X, Y, and Z components of the plastic strain tensor for instantiation number 0 due to the strain state of uniaxial that corresponds to folder 0. And we will get these for every single instantiation and for every single strain state. One thing to note about this is that we first have a line that corresponds to max compression, and then we have a line that corresponds to max tension. And these are the final max compression and max tension cycles. Because the plastic strain tensor conserves the volume, we should expect that EP11 plus EP22 plus EP33 is almost 0. So as a sanity check, if we type in sum of these columns, then we get a very small number. So this is just another sanity check that we are in fact calculating what we expect that we're calculating. And this is also true for the max compression point. And the shear plastic strains are then very, very small, of course. So because this folder has 94 subfolders, this is taking a while to do. So let's catch up when this is all complete. We now have Fips calculated for all the folders. So let's make sure that this is complete for folder 94. And it is in fact complete because we have all the files that we need here. So the next step is to volume average these Fips. So we will go back to the volume average fips.py script. We will change the directory once more to multiaxial fatigue. Change number of instantiations to 10. We'll calculate the volume averaging for the Fatemi-Sosi FIP, and we will do this for the subband scheme. Set gamma plane simulations to true. And once again, specify num gamma plane folders to 95. Hit save. So now what is unique about gamma plane simulations being true is that call averaging will read in the subband info not from one of these individual folders, but instead from the instantiation data folder. And this is much more efficient because we now just have a single copy of this file instead of replicating it, the same file, in each one of these numbered folders. So let's execute this script. type in Python volume average Fips. This will once again print out the folder that they're currently in. And you can see that if we start at folder 0, each one of these instantiations will take a few seconds to run. While we are here, I wanted to go back and note that we have a special printout here when we volume average these Fips, and we get the output of not only the highest subband averaged Fip in that microstructure, but also the location. So these numbers are indexed at 0. But basically what they indicate is that for this microstructure, the highest Fip is in grain 290, slip system 9, layer number 6, and subband number 22, because we index at 0. While these folders are slowly being populated by the file that contains the subband averaged Fips, let's go through the gammaplane.py script. We'll start with the main function. It has some of the same variables we talked about previously. The first one is directory. That simply points to the multiaxial fatigue directory. numFips extract specifies how many of the Fips from an entire simulation batch folder we want to extract. Right now it is set to 50, so what this means is that when we run this script, we will go in and we will extract the 50 highest Fips from this entire ensemble of 10 microstructures. We will then specify numRead top Fips. So this will specify how many of the highest Fips from each batch simulation folder we should consider when we create our ISO-Fip contours. The way the script works right now is to first locate in the X and Y where each simulation folder resides. So each one of these dots is one of the 95 folders. Then the response surface is the average value of the 10 highest Fips. And with that information, with the X and Y position on this plot, and with the Z, which is the average value of the 10 highest Fips, we use that information in the Gaussian process regression model to interpolate between the points and create these ISO-Fip contours. We specify Fip type and averaging type as before, and then we have three functions that we call: plot gamma plane locations, get gamma Fips, and plot gamma. So this first function, plot gamma plane locations, does not do anything with the Fips. It simply looks to see where we are on this gamma plane. The reason for this function is that when you first try to create a computational gamma plane, you will realize that you're not really sure what strains you should apply in the X and Z to evenly populate this plane. So what I did at the beginning is I ran simulations in uniaxial, equibiaxial, and pure shear, because I knew these would get me locations along the top, bottom, and horizontal boundaries. But then you kind of need to get creative and figure out what strains will get you where. So what this means is that this function, plot gamma plane locations, will plot nothing with the Fips, but just where you are in terms of the X and Y positions. So let's take a look at this first function. The first function that is read in this function is read average EP tensor difference. And if we go over there, what this function does is it looks for the EP underscore averaged CSV files that contains the macroscopic plastic strain tensor for each instantiation. It reads this in, and then it averages it over all 10 microstructures. So then the end result is that for each folder, we get one plastic strain tensor. This information is then sent to the function called getXSPlastics. And this basically just solves the eigenvalue problem, because we need the principal plastic strains to locate this simulation folder on the gamma plane. The rest of the function simply plots these on the gamma plane. So this we can actually execute right now. The Fips are still being volume averaged, so for the sake of the demonstration, I will go to the gamma plane.py script and I will comment out these last two function calls that we will talk about in just a second, but for which we need to get all the Fips volume averaged. So let's open up another command prompt in the meantime, and I will just put this over this first one, and we need to navigate to the source directory that has these functions. So everything here is good to go. So let's execute Python gamma plane. We get an error that dir loc is not defined. Oh, I am missing this definition at the top. So this will be included when you run this script, when you download these files from the GitHub. Let's execute this again. So this is much quicker. It's going through each folder and reading those CSV files. So now we should have a new plot here. So we have Prisms gamma plane ensemble test locations. So this is the plot we just generated. Let's pull this up next to this Excel sheet. And what we're seeing here is that for each of these 95 locations, we essentially just plotted where it resides. So the uniaxial state of strain is both case A and case B at the same time. So these 9 red circles correspond to folders 0 through 8. The blue triangles at the bottom here correspond to these equibiaxial states of strain, and the green squares correspond to the folders 19 through 28 along the horizontal boundary. Then these other case A and case B locations, these populate the remainder of the gamma plane because we want an equal distribution. We want to equally cover all the locations here. So this is sort of a trial and error type of approach because we can't know for sure what simulation we run at some combination of strain at x and z. We don't know beforehand where that's going to exactly put us. So what this first function does is it simply plots the locations. It doesn't do anything yet with the Fips. It just tells us where we will appear on the gamma plane. Let's look through these other two functions that we can now uncomment. The next one is called getGammaFips. So let's scroll up and look at that. And what this function does is it essentially extracts the highest Fips from each simulation folder. You will recall that these Fips take a long time to read. So what we want to do is to have these stored somewhere so we can really quickly change the settings on the gamma plane and generate a new plot. This will first make a new folder called Pickled Ensemble Fips in this Multiaxial Fatigue folder. So once we run the script, you will see that here. What this will do is it will go through all the folders and it will read the .p file that has the subband averaged Fips. It will then read these for all of the 10 from this .p file and save the top 50 because that's what we specify in num Fips extract. So this we'll call the read pickled Fips function, and that is very similar to the one that we saw for compile and plot Fips where we read in the Fips. Let's go through the last function called plot gamma. So this will go ahead and plot our gamma plane. The first function is called compile statistical info. What this function will do is it will first read the gamma plane Fips. And read gamma plane Fips will look for the folder pickled ensemble Fips and will read in the Fips that we just stored. It will also read the EP_averaged file that determines the X and Y position on the gamma plane. it will once again solve the eigenvalue problem as well. Once we have the x and y positions and the Fips, we will split these into case A and case B locations. So these are defined at the top of the script here. One thing I wanted to mention is that getXSPlastics computes the eigenvalues of our plastic strain tensor. However, users might note that when we look at one of these files, for instance 13, we essentially already have the principal plastic strains as the 1, 1, 2, 2, and 3, 3 values. Nonetheless, we still want to run this to be sure that we get the principal plastic strains. So once we are finished compiling the information for the plane, we then average the Fips over the top 10 values, or however many we specify in the num_read top Fips. We then enforce continuity at the top edge of the gamma plane. So there's more detailed information about this in the publications. But what this means is that to make sure that we have continuity at the top here, we can do something where we add the information from the uniaxial state of strain to the case A or case B. So what I do here is I found that if we add the case A information to case B contours, this gives us a better fit and better looking contours in the isofip gamma plane. So this is what happens in the get case A, case B transition. This is the first location in which we call the Gaussian process regression model. The last function is called plot contours. In this function, we once again initialize a Gaussian process model. There's a lot of items here that basically determine the extent of the gamma plane in the x and y directions. We create a grid and we take the response, the average value of the 10 highest Fips, and we use this as an input to the Gaussian process model. The remainder of the code here simply specifies plotting properties, but levels is where we specify what values we want to use for the isofip contours. We finally save the gamma plane. The Fips are done volume averaging, and we could verify this by going to folder 94 and checking to see that we have the subband average Fitemmi-Sosi Fip pickle files. So now we can once again execute this script. And really quickly, I'll show that we have no folder here with the name pickled ensemble Fips. So once we run this, it will first once again plot the gamma plane with the locations. But now it's going through and it's reading each one of these subband averaged Fip pickle files. So it just finished doing that in folder 0 for the 10 instantiations. Now it's doing that in folder 1. There is now a new folder entitled Pickled Ensemble Fips. And you'll see that this is reading the subband averaged Fitemmi-Sosi Fip. And as soon as it finishes with a folder, for instance right now it's on folder 2, it will create a new pickle file. And it does this for all 95 folders. So this is simply a way to speed up the rate at which we can generate new plots to make sure that the gamma plane is doing what we expect it to do. One note is that when we then read in these .p files, we can do something where if we need to recompute these, or perhaps we made an error in the volume averaging process, we need to go back in here and delete these. To be more specific, the code, when it tries to plot the gamma plane, will look for this file name, _0, _1, and so on, to correspond to each of the folders here. If the pickle file exists, the Fips will be read from here. But if it does not exist, that is when we go into the individual folders and read the .p files. We are nearly done compiling the Fips that are all in this folder. So now we should expect another figure here. I specified a relatively high dots per inch value, so that's why this picture is so big. And once we open this up, then we have the same gamma plane we reported in the Prisms-Fatigue manuscript. As I mentioned, each of these dots represents where we simulated the ensemble of 10 microstructures. We have isofip contours that very closely match the isolife contours formulated by Brown and Miller. Let's run this again to see how much quicker it is to make the plot this time. This first set is for once again, the locations. And then now we once again plot the gamma plane. So to execute this entire script, once we have the Fips compiled, takes roughly half a minute. As I mentioned, we could increase the speed at which we do this because we spend a little bit more time than necessary, perhaps to create this PNG file of the gamma plane. But I wanted this to be a very high quality figure. So this concludes the final video in the introductory series to Prisms-Fatigue. In this particular video, we discussed how to generate a computational multiaxial fatigue gamma plane. We went through what needs to be changed in the scripts calculate Fips.py and volume average Fips.py, and went through the entire function. Thank you for your attention, and I'll see you next time once we periodically release new videos on new features for Prisms-Fatigue. Please let us know if you have any questions and see the video description for our contact information.